Hello and welcome back to the playlist series on linear algebra. So last time we looked at subspaces, and so today I will be finishing off subspaces with a final proposition, and it goes like this. So if we let W1 and W2 be subspaces of a vector space over a field F, then the intersection W1 intersection W2 and the sum of subspaces, which is W1 plus W2, are subspaces. So let's have a look at the proof. So the proof's quite simple. It goes like this. So for the first part, we have that for the intersection, we know any subspace, W1 and W2, we have that the zero vector is contained in W1, the zero vector is contained in W2, by definition of the W1 and W2 being subspaces. Therefore, this by definition, this tells us that hence the zero vector is in the intersection. Okay, so the intersection follows this property. Secondly, so this is the proof of the intersection. Secondly, if we take any x and y, if we let these be in W, so if you take x and y in W1 and W2, then this tells us that x and y are in W1 and x and y are in W2. Hence, this will mean that x plus y will also be in W1, since W1 is a subspace, and x plus y will also be in W2, because W2 is a subspace, and we know by the definition that it's closed under addition. Hence, since x and y are in W1 and x plus y are in W2, this implies that x plus y are in the intersection. Okay, and finally, we have to show that it's closed, the intersection. So we take any A in the field and we let x be in, an arbitrary element x be in the intersection. Then again, we know that A times x is in W1, since W1 is a subspace, and we know that A times x is in W2, because W2 is a subspace. Therefore, this implies that A times x is in the intersection. Okay, this is by definition. Okay, so we've proved the first one. Secondly, so this is now the proof of the sum. We have to prove that the sum of subspace is also a subspace. So firstly, we know that the zero vector is in... Actually, before I go over the addition, it's a good thing I give the definition of what I mean by the addition. So I'm going to say W1 plus W2. I'm going to say that is going to be defined as the set of all x1 plus x2 in V, such that x1 is in W1 and x2 is in W2. Okay, and W1 and W2 are subsets of V. So given that W1 is a subset of V and W2 is a subset of V, and they're both vector spaces. Okay, so firstly, we know that the zero vector, which is in V, which is equal to the zero vector plus the 0 vector, okay, because the 0 vector leaves vectors unchanged. And we know, because these are subsets of V, we know that W1 must contain the 0 vector, and W2 must also contain a 0 vector. But if you've done a bit of group theory, then you would know that W1, so let me draw a little sketch here for you. So here's V, okay, here is W1, and here is W2, okay. Now, let me just explain. These cannot possibly be disjoint, okay, they can't possibly be disjoint subsets, because for any subspace, it needs to contain the 0 vector, okay, which means in topological terms they are not disjoint, so they're not essentially like Hausdorff spaces, which means that they must have at least one point in common, okay, because this point has to be the 0 vector V, okay, so they must contain the 0 vector. So we know, so this is on the boundary of the subspaces, okay, so this is W1 and this is W2, so we know that they must contain the 0 vector, okay, and since the 0 vector is equal to the 0 vector plus the 0 vector, this is also in W1 plus W2, and by group theory the 0 vector in a group is unique, okay, so there's only one identity, there's only one 0 vector under addition, okay, so we know that this is in the sum, okay, so that's the first one. Secondly, if we say, so let x and y be in W1 plus W2, then by definition of W1 by W2 plus W2, this means there exists an x1 and a y1 in W1, and there exists a x2 and y2 in W2, such that x is equal to x1 plus x2 and y is equal to y1 plus y2, okay, so this is in W1 plus W2, okay, we know this from the definition, okay, so if x and y are in W1 plus W2, then from the definition above there exists an x such that x is x1 plus x2 and a y, and there exists a y and y2 such that y1 plus y2 is in the sum, okay, is in V, okay, okay, so we know that, right, so we know that, and then, so when we take the addition, so we take these, so then we have x plus y, this is equal to x1 plus x2 plus y1 plus y2, which is equal to x1 plus y1 plus x2 plus y2. And we know that this is in W1 plus W2 by definition, okay? So we know that, okay? So we've just shown this because we take an x and we take a y in the sum, and we know that there's at least one x and one y in W1. We know that there exists at least an x2 and a y2 in W2. We express the sum, and because we know W1 and W2 are subspaces, we know it's closed. Okay, so then finally we'll take our final example. So if we let A be an F, our field over the vector space, and we let X be in W1 plus W2, we know that there exists an X1 in W1, and there exists an x2 which is in W2, such that x is equal to x1 plus x2, since x is in the sum. And therefore, if we take a times x, this is equal to a times x1 plus x2, which is equal to a times x1 plus a times x2, because w1 and w2 are subspaces, so we can distribute. Okay, and we know that this is in w1 plus w2, okay, because a times x is in w1, a times x2 is in w2, and by definition this is just another element, say x star, this is another element, say y star, and you take both of them, you add them, and by definition this is in the sum. Okay, so we've proven these two properties. These are useful properties, and we will be using those in the future. Okay, so in the next episode we're going to look at this again, and we're going to look at bases, okay, and basis and spanning. Okay, thank you for watching.